A bootstrap distribution is an attempt to simulate the process of finding a sampling distribution when we don't have access to data for a whole population. So recall that in a sampling distribution, you're pulling random samples from a population, calculating a sample statistic like mean, for example, from each of those samples, and then creating a distribution of means. A bootstrap distribution is very similar. It's intended to simulate a sampling distribution. And the only difference is, in a sampling distribution, it's assumed that you have access to a data set that represents a whole population. But that's a very hypothetical situation because most of the time that we're interested in statistical inference, it's because all we have is a sample, and we're interested in answering the question of what that sample tells us about the population. So this is a more realistic situation that we're getting into now. And what we do is we still find a sampling distribution from a population, but we have to make up the population. So if this is our sample, and this is a sample of size n equals 6, then we pretend that the population is just a whole bunch of copies of that sample. Notice this is identical to my sample, and then I copy it again, and I copy it again, etc. So that we pretend the population consists of just many copies of the sample. How many? It doesn't matter. You could say infinitely many if you wanted to, but we don't have enough space to write infinitely many copies. So we're settling for what looks like 9 copies in this example here. Now, this might seem a little simplistic at first, but if the sample is all the information we have, this is the best we can do to estimate our population, and it is going to help us to estimate the variability of that sample statistic, right? When we pull repeated, independent, random samples from this population, what we're really interested in getting at is how much does that sample mean, or whatever the sample statistic is that we're calculating, tend to change from one sample to the next. So what we're going to do now to get what we call a bootstrap sample is take a random sample from this pretend population. We match the size of the original sample. So a bootstrap sample, if my original sample was n equals 6, my bootstrap sample needs to also be n equals 6. And even though we've already established that humans are not effective at selecting random samples, I'm just going to pretend to be a random sample generator here and go through and select what looks like an arbitrary set of figures. So that this is a random sample of size n equals 6. And here is what my bootstrap sample looks like. Notice that everyone in my bootstrap sample was in my original sample, but not everyone in my original sample is necessarily going to show up in my bootstrap sample. The way that they can differ from one another is by having duplicates. I have a duplicate of this frowny guy. I also have duplicates of this woman with hair here and no arms, it looks like. So the only difference between a bootstrap sample and the original sample is that a bootstrap sample may have duplicates, and if it has duplicates, it's also not going to have every individual represented. So in my original sample, the ones that didn't make it into my bootstrap sample are this tall, smiling guy with the straight arms and this one with, it looks like lips and some hair on the top of his head, right? All right, now this is just illustrative. We're not calculating an actual quantity from each of these people, but let's go ahead and see what taking a bootstrap sample from an actual data set and calculating a statistic from it would look like. In our first example, we are going to find a bootstrap distribution for correlation. So the particular statistic we're going to calculate is the correlation, and in this case it's the correlation of ages of husbands and wives from heterosexual married couples. And let's suppose we're also willing to consider this to be representative of all heterosexual married couples in the US, even though they were all taken from one county. So that is a questionable assumption. But for the purposes of this exercise, we will say that that's our population. The way that we create a single bootstrap sample, if we think about what we did in the previous example, we made lots and lots of copies of our sample and said that's the population. The way that we can pull samples following that same principle is that we do what's called sampling with replacement. With replacement simply means that if we're pulling from our original sample, we take one and we mark it down, and then we put it back into that sample so that it can get drawn again, right? So that's sampling with replacement, and this sampling will be done from the original sample. Now, because our data set, our sample consists of 105 married couples, we need to make sure that each bootstrap sample also has 105. So we're going to get 105 couples in each bootstrap sample as well. So that's just how we get a bootstrap sample. And then from this sample, we're also going to calculate a statistic. So what this diagram down here is showing us is that our original sample here on the left, that original sample is our 105 marriage licenses. And I can calculate the sample statistic. This is a correlation, so remember we call that R. The correlation of a sample is R. The correlation of a population is that Greek letter rho. So now from my original sample, I get my bootstrap samples. So that's this process here is describing how I get these bootstrap samples. Each of these is sampling with replacement. So each of these is n equals 105, sampling with replacement from the original sample. And then from each of those samples, I calculate that bootstrap statistic R again. These R's are going to be different, so this R is going to be different from this R because the original sample gave us one correlation. Each bootstrap sample is going to give us a different correlation. They won't necessarily be really far apart from each other, but they won't be the same value coming up over and over again. Then I take all of these R's, so I get an R from here, I get an R from here, I get an R from here, and this bootstrap distribution is going to represent all of these different correlations. So this distribution is going to be of the sample correlation R. In this case, we would use this same diagram to describe bootstrap distributions for X bar, bootstrap distributions for P hat, even for a difference between two means like X1 bar minus X2 bar, or a difference between two proportions like P1 hat minus P2 hat. So these are just different contexts. In this particular case, we are talking about correlation just because that is what we said from the start, correlation, right here in the description.